let's start with the problems from the book.
Wait,
Okay.
is this supposed to be done?
So when you look at, and this is kind of what we talked about yesterday, when you look at that problem 52, and you have to be able to differentiate, and this is kind of a tough conceptual thing, in terms of what's the direction of the electric field, okay? And you always have to remember that the direction of an electric field is what a positive charge is going to feel. So if you look on problem 52, okay? So you got a 5 nanocoulomb charge, exists, okay, uniform field. At what point along the x-axis would a proton and an electron experience no net force? Okay? So here's the story. So you've got a positive charge particle here with 5 nanocoulomb, right? Cool. The electric field is going this way. Don't worry about the effect that the electric field is going to have on that positive charge. We're looking at what it's going to do to the proton and the electron. So you have the value of the electric field. You're talking about a proton or an electron. Knowing the value of the electric field, which is 4,500 newtons per coulomb, what can you find? Knowing that it's an electron and a proton. You find the force. Effect. Bummer. Okay? So you can find the force. Now, is the force on an electron and proton going to be the exact same?
No. Yes.
In terms of magnitude.
Yes.
Right? In terms of magnitude. Right? Okay, in terms of magnitude.
He forgot to take his medicine.
Okay. Now, here's the story. And at what point would the proton electron experience no net force? Okay? So let's just play the what if game. Let's say that you put the proton over here. You don't know which side. Pick a side. Pick the right side. So if you put a proton over here, okay? If you put a proton over here, what's that going to feel? It's going to feel pushed that way, right? Well, what else is it going to feel? So it's going to feel pushed that way, and it's going to feel a force pointing in that direction also from the electric field. But if I put it on the left side, then it's going to feel a repulsion, which is pushing it to the left, but the force from the electric field is going to push it to the right. Right? So you just have to be able to think through it. Okay, hey, what if I put it in these different sides? So a proton needs to be on which side? The left or the right? Left side. Now, you want these things to balance out. So you want the force from the electric field to equal the repulsive force would be F equals K Q1, Q2 over distance squared. Okay? These two things have to balance each other out. So here's always the $1 million question. Okay? And this is the most common mistake that's made on these type of problems. You have that 5 nanocoulomb charge, and you have the proton. Okay? Which one goes in here on the FEC? The proton or the 5 nanocoulomb charge?
The proton.
Proton. Why?
It feels
The proton is what's feeling the effect from the electric field. Okay? we're not worried about what the 5 nanocoulomb charge is going to feel. Is it going to feel something? Yes, not part of the story. Okay? 5 nanocoulomb charge is anchored. So you have to remember this. This is that Q value is what's feeling. Here's the same idea. If you look at the gravitational force equaling mg, do I put in the mass of the baseball that's going to fall, or do I put in the mass of the earth? Or put in the mass of the baseball, because that's what's going to feel that weight. Okay? So the same thing is going to happen here. I'm going to put in the charge of the proton. Now, here's the beauty of this. You set these two things equal. So this is EQ, charge of the proton. It's going to equal K, Q of the proton, times that charge on that 50 nanocoulomb, or 5 nanocoulomb, divided by d squared. What's going to happen to the charge on the proton? This is going to cancel out. Okay? So you actually didn't need to have that. So now you know what the value of the electric field is. You know what that is. You know what K is. Solve for distance. Okay? Yes?
What does Q2 say?
That's just the charge on that 5 nanocoulomb.
Oh,
Okay? Shannon?
Okay, we have the proton on the left, right?
Yes.
Okay, so it feels repulsion to the left from the proton. But those feels
Whoa. Back up. You said the proton feels repulsion from the proton.
from the center charge.
From the 5 nanocoulomb.
From the 5.
Yes.
So it feels repulsion to the left. But don't you feel with force is still going to the right?
Mhm. So just back up. Back up the bus. Keep these two ideas separate for now. Okay? Just worry about you have a 5 nanocoulomb charge here. You have a proton over there. What's the proton going to feel?
Repulsion.
Push to the left. True?
Sure.
Okay. Now, block out the 5 nanocoulomb charge. It doesn't exist. Don't worry about it. All you know is that you have a positive charge in an electric field that's pointing to the right. So, if you have a positive test charge and that electric field is pushing to the right, what's that going to feel based upon the electric field?
Repulsion to the left. Yeah.
No, that positive charge, if that electric field is pushing in this direction, that positive charge, that proton, is going to feel pushed to the right.
Okay.
So it's going to feel a repulsion to the left and a force from the electric field to the right. And they're going to cancel each other out.
Okay.
That's how it can be no net electric force. But if I put it over here, then it's going to get pushed and pushed. Okay? Does that make sense? Now, here's the tough conceptual part. I'm going to tell you straight up. This is the toughest part. Where do you put an electron? Now, here's your gut feeling. You think, oh, okay, right. If the proton is over there and it feels no electric field, I should put the electron on the other side because that has a negative. Okay? I'm telling you, that's a bias that you have. But start over from scratch. Start over from scratch. You got a 5 positive 9 coulomb charge here. Let's say you do put that electron over there. What's that going to feel? It's going to feel an attractive force to the left. Okay? True? Now, forget the 5 nanocoulomb charge exists. Now you're going to have an electric field pointing to the right. Okay? That is the force. That's the value of the electric field. That's an electron. So, based upon the electric field, what is it going to feel? Pulled to the left. So if I put that electron over there, both of these are going to pull it to the left. No bueno. Okay? But I put that electron over here. Yes. Now they're going to cancel out. So the position of the electron and the position of the proton is the exact same. Okay? So your answer to 52 should be very much, it should involve a 1, but should be less than 1 in meters.
How much more do you want?
Wait, over
Yeah.
Oh, I thought they were saying 54.
Anything but listening, anything but listening.
Yeah, Big Mike, that is a skill you do not possess.
I can listen.
Dang.
You can.
Doesn't.
Okay. So on 52, I'm begging you, just do not write down a number. Somehow indicate which side that is. Okay? Because if you just put down 0.1 meters, I have no idea where that means. Okay? Make sure that you somehow indicate where that is. Okay. Your answer to 54 should be a fraction.
But you hate fractions.
I do, but
Wait, what'd
or
you
you
say?
can put it as a decimal.
What if it's like
It could be a negative fraction.
Like,
So like what kind of fraction?
yo, it could be any number you
I
want.
don't want any kind
well,
of
yeah, but I
fraction.
got the right.
I don't want no vague
Okay.
answer. That
Now, the whole key to 54, okay? The whole key to 54 is that you're going to be talking about the force. And when you're talking about force of charged particles, what happens to the distance? It gets squared. So if you double a distance, it goes up by a factor of 4.
I got something right.
Just keep that in mind. Now, 56 is a very, very interesting question. I like 56. So let me kind of paint you this visual about what they're trying to say on 56. So model a pollen grain is a sphere of carbon 0.1 millimeters in diameter. Okay? Now, to give you some perspective, 1 millimeter of thickness would be the thickness of your fingernail. Okay? This way, like this edge. Okay? That's 1 millimeter. Right? This is 1/10 of that. Okay?
Pretty small.
So imagine 1/10 of the thickness of your fingernail. Very, 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 very small, right?
Yeah.
And it's going to be a sphere. So, how do you calculate the volume of a sphere?
4/3 pi cube.
4/3 pi r cubed. Okay? This is the pirate's favorite equation for volume because it's r cubed. Okay? This is radius. What did they give you? They gave you the diameter and they gave you the diameter in millimeters. Okay? All right? So, you need to do some serious conversions there. Then you can find the volume of the sphere.
That question was asked.
You also have on here the density of carbon. And they say, hey, we're just going to treat this thing as pure carbon, which makes it easy. So, once you know the density, then you can find the mass of carbon, which should obviously be a pretty small number. Okay? So the mass of the carbon should start with a 1. Okay? The mass of the carbon should start with a 1. Now, but that needs to be in grams so you can do the mole conversion. So what you ultimately need to do is figure out how many protons there are in each one. So, yeah, so you got to do some serious conversions. You got to go in grams, and the molar mass of carbon is 12.0 grams per 1 mole of carbon, And then you can use Avogadro's number. 1 mole is 6.02 times 10 to the 23rd atoms. Now, each atom of carbon contains how many protons? 6. So you need to do one more conversion to go, each atom is 6 protons. Okay? Now, what's the charge on each proton?
1.6 to the negative 19.
So each proton has a charge of 1.60 times 10 to the negative 19.
Yes.
So the total amount of charge, okay, the total amount of charge, obviously in coulombs, is around 0.06.
I like it.
Okay? That's the total amount of charge on each one. So then you're going to go F equals K, Q1, Q2 over distance squared. So the value of that force should be an GPA times 10 to the 7th. Okay? Now, think about this. Okay? Let's just think about this. So, a 1 kilogram mass weighs about what? 10. We can round it up, call it 10. Okay? So you all know what the feel of this is. Okay, you all in this class lifted a 1 kilogram mass many times. Okay? It's about 2.2 pounds. Feels pretty heavy. So what we have here, and this is the study part of this. So here are these 2 pollen grains. And they're separated by a distance of 1 meter. So here are these 2 pollen grains. This is what I want. The reason I assigned this problem is more philosophical and do still use the sense of science. Okay. So these 2 protons, or these 2 pollen grains. And this is just 1 pollen grain. This isn't like a whole bunch of pollen grains. This is 1 pollen grain here, 1 pollen grain here. The pure force of repulsion is about 3 times 10 to the 6th times greater than the weight of this. Okay? So here's the question. So here's these 2, 1 meter apart. You have a force in between these 2 of 3.0 times 10 to the 7th newtons. Okay? Now, if I exert a 10 Newton force on a 1 kilogram mass, what's the acceleration? So help me God if you get this wrong, or you just walk out of this room. If I exert a 10 Newton force on a 1 kilogram mass,
10 minutes.
Okay, the one. I'm gonna get 10.
okay? Let's go with 10. So here's my question.
I'd say like 9.
Here's my question. You have a force of 3.00 times 10 to the 7th newtons on a mass of 1.24 times 10 to the minus 6 grams. Okay? How do flowers even exist?
They don't.
Mother
They
Nature.
don't.
Jesus Christ.
So when there's like, God made
They don't, bro.
the seed gets planted into the ground.
Amen.
Like the flower comes out of the
Photosynthesis.
ground.
We are in a dystopian reality.
Wait, the
Yeah.
flowers have okay.
Oh, we're cooking right now.
So,
Benjamin
The
Netanyahu.
flowers, they have like
They have
Flowers have
electrons.
Oh! What'd you say, Finn?
They have electrons.
Oh, they
No,
also
they
have
don't.
electrons.
Okay, well,
Photosynthesis.
I am not wrong. I am not wrong.
Yeah, but hey, can you see
Now,
that?
What is the tangent going on?
Can you see that?
No, I just want
You also have electrons.
to.
So you have the Chihuahua cloud around those.
Ew.
Okay? Now, here's what I want you to think about. you have a very, 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 very large number of protons in there. Okay? Which means that's also the total number of electrons that you have around there as well. Okay? So the electrons feel that same repulsive force. Electrons don't like each other either. So you have the electron cloud repulsing each other. You have the protons repulsing each other. That's a lot of repulsive force. But the electrons are also doing what? They're attracting to the protons, right? So one of the questions is, why don't all the electrons collapse into?
They're far away.
No.
The strong magnetic force.
They're
Gluon.
repulsing each
like-
other.
The weak nuclear
Wait,
force.
What's the question?
What was the question?
So here's my question.
I don't know.
Now you have a magnitude of how much force there is. Okay, and again, this is a single pollen grain, 1/10 the thickness of your fingernail. And it isn't like they're in the same flower. They're separated by this far. Okay? They're separated by this far. And they experience that much of repulsive force. Okay? Now, imagine all those electrons which are really close to that nucleus. What are they going to feel? They're going to feel a lot of an attractive force, right? So the question being is that why don't all the electrons collapse into the nucleus?
Because.
Is that
So you have an electron, right? And then you have a proton. The electron is
Does that have anything to do with
true?
but then the electron is also repelled by the other electron over here. And it's
No, no.
Oh,
It's like a storm. No,
I see it.
Weak nuclear force.
Wait, and then it also
That only plays out.
Hey,
the electron is like attracted to the other
how many electrons does Spice have?
Because there's protons.
Wait.
Newton's third law?
Don't you? We haven't figured it out yet.
Oh, we know the answer.
What if it's an odd number?
Yeah.
Don't
So-
say me.
Here's this. We'll spend a lot more time talking about this.
Wait, Mar has
Is
an
that?
answer. Mar has an answer.
No, it's shush.
Mar
It's
has
not
an
that
answer.
important.
Mara has an answer.
What?
Does it have to do with bees?
Oh my god. Nathan, I'm about a 9/11 you.
Does it have to do with molecules?
We are all in AP chem, right? We all know what electron.
Mr. Bird, does it have to do with molecules?
That's sort of waves. Okay? Eventually, you decided something called the De Broglie wave function.
What?
No.
Wait, what's it called?
Hey, he's actually trying to teach right now.
How about you be respectful?
Bird, Bird, what's it called?
So it's called the De Broglie wave function. Electrons travel in waves.
No, they
Okay? And so imagine that I wrap this around, and so
Oh,
it
yeah.
has to end up where a wave overlaps the beginning and the end. So that's like one possible dimension.
Oh.
Then I can bring it closer, like this, and then it ends up like this, okay? Now notice here you've got this, it starts, goes down, so this is like two wavelengths. If I make that even smaller, the smallest I can possibly get would be what? One wavelength. So if I roll this up really small,
This is gonna be on the test.
and I get this, so notice it starts here, goes down, comes back up, and end up back where I started. So because the electrons travel in a wave function, that's as close as they can possibly get. This is
No
why
way.
they can't collapse into the nucleus, even though they have an incredibly strong attractive force. Because they have to travel in waves, so they have to complete their wave function.
So is
We'll
this on
spend
the
a lot more
test?
time talking about this.
I don't think so, right? I'm not saying that.
Okay,
Yeah, because I was gonna say.
on number 60, let's go back to 56. So if once a force to the weight of an aircraft carrier which is about 9 times 10 to the 8th. So you can either have that as like a fraction, you can have it as a percentage. If you do it as a fraction, it's about 1/30th. Okay?
What if I say the aircraft carrier weight is 30 times greater?
I can live
What
with
about a
that.
decimal?
What
I
about
can live with
scaling?
that.
What about scaling?
What if I draw
What about drawing?
relating to
What
the
about
size?
scientific notation?
Let's talk about 60, because I guarantee you there's going to be something like 60.
Wait, what was it?
So you got
I think the final answer.
2 centimeter diameter disc, 1 millimeter apart. They are charged to 10 nanocoulombs, so it's the electric field strength. So if that electric field strength is wrong on A, you have no chance of solving B.
Nice.
So your answer to 60A should be a pretty decent GPA times 10 to the 6th.
Define pretty decent.
Not quite 4.
He
So
said
like,
times-
so like
times
that,
ten to-
like that.
You're a B.
Okay?
Hey, you like to play
Now,
that?
to get B, a proton is shot from the negative disk towards the positive disk. What launch speed must the proton have to just barely reach the positive disk? Conceptually, that's like me throwing a baseball up, and I'm trying to figure out how fast I throw it until it just approaches the ceiling. So when it just approaches the ceiling, what's the final velocity going to be? Zero. So you're trying to find the initial velocity so that as it goes across. Now, here's what I want you to think through. So you've got a positively charged disk and a negatively charged disk. Okay? So the whole key on 60 says one thing. It says a proton is shot, but we want it to slow down.
Yes.
So on 60, it says a proton is shot from the negative disk toward the positive disk. Why would we shoot it that way?
Because the other one attracted by the negative.
So you have two things that are going on.
You said what?
If I shoot that positive charge,
Say anything. I haven't done anything.
you were thinking about it.
Jack, you're getting kicked out, Mike.
I did always leave.
Can we
You're going off the island.
Shaq,
So, as that gets shot out from the negatively charged plate, it does two things. It's attracted back to the negative plate,
Yes.
and
It's pushed.
is pushed back from the positive. That combination is going to make it slow down. Okay?
See.
Because if I shot it from the positive to the negative, what's it going to do? Then it's going to speed up. Okay. So once you find the value of the electric field, then you can find the force using FEC. Okay, because now you've got your E value, you know the charge. You find the force. Once you know the force, and you know, I swear on the test tomorrow, if I look up at some point, if you're not doing this, I'm just going to be, I don't know what I'm going to do. Okay? So,
Trash out.
yeah, tomorrow, if you don't use that, something's wrong.
Uh-oh.
Yeah, tomorrow is the test.
Are you serious?
Oh yeah.
Bro.
No, I got it. I'm lucky. I know. No, I know. I got it. What if I take the
Why
test?
do you think
He's about to rage.
Well, about not.
He's sorry.
Is
about
Wait,
that.
tomorrow
It's
is
Thursday.
So, Berg, you said this one, you said this one's guaranteed.
What if I take it?
What other
Thursday.
questions?
What if I take it like 3 weeks from now?
Yes, we did.
Everybody's talking.
You would you prefer I have them all on the same day?
No.
That's like
I
my
think we
point.
take all of this.
Stop it, Caleb.
Okay. So, your answer to 60B
No, fuck you.
should be something times 10 to the 5th meters per second.
What?
10 to the what?
10 to the 5th.
Hold on.
Something times 10 to the 5th.
What?
What units?
Meters per second.
Oh.
Elliot,
What was your
That's
estimation for
last week.
60A?
Transferred it to
It was.
a decent GPA times 10 to the 6th.
Oh no.
Consider 1.8.
No.
Okay, that's pretty.
Hey, just double
That
that,
is
bro.
not decent.
That's really bad. Actually. That's
What? Oh,
Like, that's
big.
like D's and everything.
I was gonna say, so you said 60 was most likely going to show up on the test.
Some version of that, yeah.
What about like any of the other questions.
That was my question.
Can we like
Just-
list the
just chill out.
test
We're
questions?
gonna-
Hey, Doctor.
Yeah, just give us the. Yeah.
Can you remind me of what's happening?
You guys are going over the rest of the assignment.
It's on your sheet.
He's so done.
It's
It's on your sheet.
On the other sheet.
So, on 60B, your acceleration, okay, that might be a problem. Your acceleration, once you use, should be something times 10 to the 14th.
Ooh, on 61?
No, on 60.
Oh, my fault.
Okay. 61 is a similar type idea. Okay?
What I got.
You have the launch velocity, you know a distance, what's the electric field strength. So you kind of, 61 is kind of the reverse of 60. Okay? So you've got to find the acceleration, and then you got to find the force, and then plug that into Fek. Okay? On 62, promise you, there's going to be something like 62 where you have like an angle involved. Okay? Promise you. Absolutely promise you. Now, it all hinges off of one idea. If you know the mass, what's the one thing that you can always find?
Gravity.
You can find the gravitational force, which means you know that side of the triangle. Okay? That's the one absolute.
Well, we can find
Then,
tension.
if you know this angle or some combination of that, you can either find the tension or you can find the electric field strength. Okay? Promise you, if you hand in that test tomorrow and you haven't done something with an angle and that gravitational field is balancing, is acting upward, and that's that hypotenuse of that triangle,
Definitely done something.
you have done something horribly wrong.
That's right.
What?
What should my force be on 60?
Your force? Something times 10 to the negative 13.
Oh. What? Mr. McKinley.
What does
So,
that say?
you said the velocity was like an energy BA.
FG. That's in G.
No, I never said something about
Yeah,
it.
it's
I
supposed
just
to be
said
gravity.
something times 10 to the fifth.
So
Either
he's
like
doesn't
two
know
times- two times
He's
the
like
I,
Okay.
I just multiplied.
okay. So your answer on 62 in nanocoulombs should be between 5 and 10.
Hey.
Hey.
Okay?
Yeah, that's what I-
So on 62,
Come on.
on 62
But that's the whole
in
cycle.
nanocoulombs is between 5 and 10.
Oh.
Okay? Cool with that one. On the spring problem, okay? On the spring problem, your K value should be very close to 1 Newton per meter.
Hey.
Okay? Because if that's wrong, everything's going to be a train wreck. So here's what's here's kind of this visual about what's going to happen on B. So here's this spring, and you're going to put these two positively charged particles on it. And the spring is going to go from 4 centimeters out to 4.5 centimeters. So right away, what do you know about the charges on the end of the spring?
They're the same.
They're the same. These are going to be both positive, both negative. Okay? Because if they were oppositely charged, what would the spring do? The spring would compress. So you know these have to be oppositely, or the same charge, because it's repulsion. So you kind of need to approach this from two different perspectives. One, you need to express it, or approach it from F equals Kx. Now, you know what the K value is. You have that number.